So I had a request to take a look at a few problems from the review content for the final exam. I'm going to start with, these are the questions on writing these functions as a power series. And I think some of these questions are maybe a little bit more complicated than what we did in class because they've got some extra variables, but I want to go through the basic process with you of how we write these as a power series. So I'm going to start with number 1 here. So write this problem down. You've got 6 over 1 plus 7x to the 4th. Let me go back to my whiteboard here. So the function we're looking at was 6 over 1 plus 7x to the 4th. And what you need to observe is that the structure of this is very similar to the infinite sum for a geometric series. Remember, the infinite sum for a geometric series is a over 1 minus r. So if we have those 3 terms, we can write it in this format by doing some different algebraic manipulation. The lower left corner needs to be a 1 to start off, and in this case, it already is. So I'm not going to have to do anything with that. 6 is going to be my a term, and then r is this number this term in the lower left corner, but there's a minus sign here. So let me write this out. So a is going to be 6. And then r, because there's a minus sign in the formula, but it's plus here, this is going to be negative 7x to the 4th. So remember, your geometric series, the basic format is a r to the n. So we're just going to put all that together, and we're going to say 6 times negative 7x to the 4th to the nth power. And we'll start this at n equals 0. If n is 0, my initial term is 6, which is what we'd get if x were 0. So I think we're okay there, up to infinity. And then that's basically it. That's all I'm asking for. It said in the directions to find the interval of convergence. For this one, it's a little bit complicated. Well, I don't know, it's complicated. It's just a little bit more algebra. But what you would do is remember, for this to converge, absolute value of r has to be less than 1. So what you would do is you take your absolute value of the negative 7x to the 4th and make that less than 1, and then you would solve that for x. I'm not going to worry about that right now. Like I said, if it's for us, it'll just be x. It won't be anything more complicated than that. Let me go ahead and take a look and see what else is on this page to see if there's another one I want to go over here. Pause this for just a moment. All right, here's a couple others we can take a look at. I just Googled and I found a few others that looked like some interesting questions. So there's 2 here. This is on I just Googled and found these, but this first one here, it says find a power series representation for the function x over 1 plus x squared. So what they did, you've got the 1 in the lower left corner like you need. So the only thing they had to do is figure out what the r value was. So the r expression, you notice, was negative x squared. So because this is plus, right? So it's plus, so plus is a negative negative, so that means negative x squared is your common ratio. So they wrote this as x times negative x squared to the nth power. And this is fine for me for the final exam. You don't have to simplify this. You don't have to write it this way. They're writing it this way so you can see that's an alternating series. But I'm fine if you want to leave the negative in there. Here's another one we can look at, 1 over 7 plus 2x. Let's take a look at that. Let me go back to my whiteboard here. And we'll get rid of that. I think I got to erase this stuff. So let me see if I can get rid of all this and make some space. All right, so the function they gave us was, I forgot what it was. Let me go back to it. It was 1 over 7 plus 2x. So let's look at that. 1 over 7 plus 2x. So you'll notice that, remember, it's got to be in this format, a over 1 minus r. So we don't have a 1 here, we have a 7. So how do we get rid of that? The quickest way to do that is just divide everything by 7. That's just like multiplying it by 1. So if we divide everything by 7, the function now becomes 1/7 over 1 plus 2x over 7. And then it's in the format I need. So a is the 1/7, and r is going to be negative 2x over 7. So if we put that together, we get 1/7 times negative 2x over 7 to the nth power. And as I said, for tomorrow, for the exam, this is good enough. You don't need to worry about trying to simplify this. I don't need the negative 1 in the front or anything like that. This is all I'm looking for these questions. So don't go too in depth. And there's plenty in chapter 9. I think the book ones might be better for you to practice with, but if you go to chapter 9, want to say it was section 9.9. There's quite a few in there that you can work with. And then the other ones I wanted to look at were some of these questions. We're looking at improper integrals. And so as you recall, an improper integral, this was from the end of chapter 8, and we rewrote these using a limit. So the hardest thing about these is how do you integrate them? So number one, I would say this needs to be integration by parts. You've got two functions being multiplied. 1 plus 2x is a polynomial. E to the negative x is exponential. So of course, if you remember your Lipit rule, P, polynomial, comes before exponential, so that means 1 plus 2x is going to be our u. So let's go ahead. Let me go back to my whiteboard here, and let's make some space. So we had 1 plus 2x times e to the negative x. Let's look at that. Using a different board at the house, so this is a little different than the one we use in class. A little more erasing. That's okay though. All right, so we've got, let's write that out. So the integral of 1 plus 2x times e to the negative x dx from 0 to infinity. So the first thing I'd want you to do, remember, is to write this as a limit. So we say the limit as b goes to infinity, and we write this from 0 to b, because we don't integrate with the infinity, but we can integrate with b. We're going to look at what happens as b approaches infinity. But we're going to integrate this. So remember your Lipit rule for integration by parts. So u is going to be the 1 plus 2x. That means dv has to be e to the negative x. You know, I love to use the tabular method, so I'm going to go ahead and do that. So 1 plus 2x and then e to the negative x. 1 plus 2x differentiates down to 0, so let's go ahead and differentiate that column. We've got 2, and then we've got 0. And remember, you integrate this column, so this will be negative e to the negative x. And then integrate that again, you get back to e to the negative x. So plus, minus, plus, down the diagonals, and then across. So my antiderivative here is going to be, let's do, we've got that negative there, so that's what I'm trying to be careful of how I write this. So we've got negative 1 plus 2x times e to the negative x, and then minus 2e to the negative x, and then of course the last part's the constant, but it's a definite integral, so I'm going to leave that out and go from 0 to b. So then we're going to have, remember this was the limit as b approaches infinity. Let me see if I can scroll this down a little bit. All right, so then we're going to have negative 1 plus 2b times e to the negative b minus 2e to the negative b, right? All of that minus negative 1 plus 2, well, times 0, of course, times e to the 0 power minus 2e to the 0 power. All right, so let's clean this up just a little bit. What I want you to observe is you've got a negative exponent, negative b for both of these. So these are both going to move to the denominator. So we're going to have negative 1 plus 2b over e to the b minus 2 over e to the b. Now over here, let's see, of course, that zeroes out, that's just 1. And then e to the 0, of course, is 1. So that's a negative 1. So we've got minus a negative 1 minus, this will just be 2. All right, so remember we've got the limit as b approaches infinity. So what's going to happen then to both of these first expressions as b gets large? The denominator is going to grow much faster because it's exponential. So both of these expressions, of course, are going to zero out. And then you're left with negative of a negative 3. So I believe our final answer should be 3. So we would say that this integral converges, and it does converge to 3. When we have an improper integral, we say it converges. Remember, with improper integrals, it converges as long as we get a value for that limit. And let's just double check the answer. Yeah, so an integral converges to 3. But that was the trick there, is you wanted to use integration by parts in the beginning. All right. On this same page, let me go back and look, see what other ones look interesting. Number 2 is similar. You would do the same thing, but the only difference is you're going to set up your limit from b to 0, and you're going to take the limit as b approaches negative infinity. I'm looking at number 3. I wouldn't worry about number 3. The reason number 3 is in this section or in this review is because there's there's going to be a vertical asymptote at 5, let's see, if you set 10 plus 2z equal to 0 at -5, there's going to be a vertical asymptote at that left endpoint, and that's why this would be improper. But we would integrate this using a natural log rule, right? This would just be a u substitution with a natural log. Number 4, again, would be there would be a discontinuity at 2, I believe, the upper limit, and that's why that's in this section. This would also be a u substitution. U would be the w squared minus 4. Number 5 rather would be a u substitution as well. Yeah, the rest of these look like they're just u substitutions in terms of the integration. Number 9, I believe, will be partial fractions. That looks kind of interesting. Why don't we try number 9? We've got x squared plus x minus 6. Let me come back over here. Let's erase our board here. And let's take a look at number 9 on that same page. And sorry, what I did for the whiteboard here, I just made a quick little Word document, and I just made it one page. I should have made it multiple pages. That would have been the better way to do this, but that's okay. All right, so, and there's probably a better way to erase this, but I'm not sure right now, so I'm just going to go with it. This is a software I've only used a few times this semester. Okay, so let's go back. So we were looking at the integral of 1 over, I believe it was x squared plus x minus 6, but let me double check that. X squared plus x minus 6 from 1 to 4. All right, so why is this improper? My assumption is that there is a discontinuity at either one of the endpoints or in between. Let's take a look. So if I set the denominator equal to 0, this will factor into x plus 3 and x minus 2. So we would have a discontinuity at -3 and +2. All right, so that means there's a vertical asymptote at x equals 2. So if we didn't do a whole lot with these in class, and I'm not going to have anything on the test where you have to break it into in between the interval like that, but it's okay. It's not a bad thing for us to review anyway, just the technique. So what we would do is because there's a discontinuity at x equals 2, we would kind of think of this as the integral from 1 to 2 of the function. So I'm breaking it up where the discontinuity is, and then we'd go from 2 to 4 of the same function. And so remember, when the discontinuity is at the upper limit, let's think about that. So if you're thinking about it kind of visually, if you're going from 1 to 2, you're approaching it from the left, we would say this becomes the limit as b approaches infinity sorry, not infinity, my bad. As b approaches, I just use b for everything, as b approaches 2 from the left, and we would integrate this from 1 to b. All right, and then the other one, we're going from 2 to 4, so we'd be approaching 2 this time coming from the right. So we would write the other one as the limit. Well, here, let's do it this way first. We'd go from b to 4 of the same function, and we would say the limit as b approaches 2 this time coming from the right. And these would be the two limits and integrals that you would work out. I'm not going to take the time to go through all of the steps here, but how would we integrate this? I just wanted to remind you how to integrate this. It looks to me like this would be a perfect opportunity to use partial fractions because the denominator factored, right? The denominator factored into x plus 3 times x minus 2. So we would say, okay, 1 over x squared plus x minus 6, that's a over x plus 3 plus b over x minus 2, and then clear your fractions. Don't forget how to do this. I know partial fractions will be on the exam in some form or another. So then remember, you choose your values. So if x is 2, we would have a would just 0 out, and we would have 5 times b, so that makes b equal to 1/5. And then if x were -3, the b would 0 out, and we would have -5a, so a would be -1/5. So then you'd go back and you would integrate, And I'd maybe write the b term first, 1/5, because it's positive, over x minus 2 minus 1/5 over x plus 3. And of course, those would be your natural log rules. I'm out of room here, but I think you get the idea. These would be your natural log rules, and you would use those as your antiderivatives. It's a pretty long, complicated problem because you got to integrate this, and then you got to go back and you got to evaluate both of these limits. But here's the setup for those limits. As far as the exam goes for improper integrals, it's not going to get any more complicated as far as setup goes than number 1. It'll be from like 0 to infinity or 1 to infinity or something a little bit more straightforward, because that's mostly what we did in class, and that's not a huge part of the test. There might be 1 or 2 on the test just like that, okay? All right, so hopefully this is helpful. Like I said, chapter 9, I would recommend going back and looking at section 9.9. Really review that old test. If you feel good about the Unit 4 test and being able to do those problems, then you should be fine for anything that we ask from that unit on the exam.